All right, so today's video is on something called sigma notation. So sigma notation is a type of summation. Remember, summation means addition, right? It's the answer to an addition problem is a sum. So a summation, we're going to be looking at a special kind of addition, okay? So what is sigma notation? So sigma notation is a shorthand way to write a really long sum. So if I wanted to sum the first 10 integers, remember integers are just whole numbers. They can be positive or negative. 0 is included. But if I wanted to sum the first 10, I would do 1 plus 2 plus 3 all the way up to 10. Okay, writing that all out is a little bit taxing, I guess. So in order to write the same expression in a much more concise way, we use something called sigma notation. So this symbol that you see here that looks kind of like a capital E, kind of funny, this is called sigma. And with this notation, this right here means the exact same thing as 1 through 10, adding the numbers 1 through 10, but it's a lot quicker and easier to write. Okay, so let's go ahead and look at this a little bit closer on the next slide. So this little symbol here again is called sigma. It's a Greek letter, and it is the Greek letter for capital S. So S here is standing in for sum. So our Greek letter sigma, which is S, is a sum. So the parts of the summation are sigma. So sigma again is this big symbol, the Greek letter. That tells me I'm going to be adding something up. Okay. The index is the variable that's being used here, n. So this is the index tells me what number to start at and what number to end at. So if it says n equals 1 down here, that means the first number that I want to start with is 1. And then the number that I end with will be on top of sigma. So n equals 1 to 10 means I want to start with number 1. I'm going to go all through the integers from 1 till I get to that number on top. So in this case, 1, 2, 3, and then up to 10. So I'll start at 1, I'll end at 10. The formula that our index numbers get plugged into is out in front of sigma. In this case, it's not much of a formula, it's just n, right? But that can be any type of formula. And so the way this works is that I would go ahead, let me grab a pen here. I can go ahead and grab the first number and plug it in for n in the formula, right? In this case, there's not much to do, just replace n with 1. Then I would go up to the next number, 2. 2 in for n would be 2, and I add all these together. The next number after 2 is 3, so I would plug 3 in where n is. And then I would do that to 4 and 5 and up through all the numbers until I get to 10, and that would be the last one. So basically, it's just 1 plus 2 plus 3 plus 4 up to 10. Okay, I'm just adding those first 10 numbers together. So let's try some examples where our formula is not just n. Okay, there might be one on the next slide that has that, but we're going to see how this works with different formulas. So we're going to look at these one at a time. We're going to start with this top one here. So my index is I in this case. That just means that I is the number or the variable in my formula. And I'm going to start with I equals 1. I'm going to go up to I equals 7. So I'll start with 1 and I'll end with 7. So if I plug 1 in here into my formula, that is squared, I'll get 1 squared. Okay. Then again, how my index works is it goes from 1 to 2. It will just go in order of the integers until it gets to number 7. So the second number I'm going to plug in is 2. So 1 squared plus 2 squared. I'm just replacing these i's with my number, so everything's going to be squared. Plus 3 squared, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. Okay. Now notice here, it just says to rewrite as a sum, so we're not going to actually add these up on this slide, but you could, the answer to this would actually be the sum of that. You would actually want to square each number first and then add all those up to get it. But since it just says to rewrite as a sum, we're going to leave it as a sum here. On the second one here, we see that my index is n. It starts at 2, and we're going to start at 2 and go up to 5. But n here is, again, just n, so I don't really have much of a formula here. So I just replace n with 2, then I replace it with 3, then 4, and then 5. And 5 is my stopping point, so I won't go on. Remember, just put a plus between each term, okay? On this one, I have a little bit more of a formula, 2k plus 3. I'm going to start at 0 here, and I'm going to go up to 6. So 0 is the first number I plug in for k, so just 2 times 0 plus 3. Okay, so that's just this term here, right? Now I'm going to add on, I'm going to go from 0 to 1, so 2 times 1 plus 3. Then I'm going to add on 2 times 2 plus 3. Okay, and then 2 times 3 plus 3. And then 2 times 4 plus 3. Whoops. And then 2 times 5 plus 3. And then 2 times 6 plus 3. So those would be all of my terms. I always start at this number and end at this number. They just go up by 1. I plug each number in and then add them all together. So on this one, I have 2 to the power of a. My a is going to start at 1 and it's going to go up to 4. So 2 to the first power plus 2 to the second power plus 2 to the third power plus 2 to the fourth power. So that's how summations work. That's how sigma notation works. It tells me I'm going to be summing up some numbers. I'm going to start at the bottom number and end at the top number. Just plug each number between those two numbers in and add them all together. Okay. So this one, notice it doesn't just say to write it as a sum, it says to evaluate each series. Okay, remember when I add a list of numbers together like that, it's called a series. So this time, we're not just going to write the sum, we're also going to evaluate it. So my index starts at 1 and goes up to 5. My formula is n squared plus 4. So I'll have 1 squared plus 4, plus 2 squared plus 4, plus 3 squared plus 4, plus 4 squared plus 4, and then plus 5 squared plus 4. That's my stopping point, was 5. So I started at 1, I ended at 5. It just goes up one number between each term. So now I can go ahead and evaluate this. 1 squared is 1 plus 4. 2 squared is 4. I'm just going to go ahead and do the squares first before I add. 3 squared is 9. 4 squared is 16. And 5 squared is 25. Okay, and 1 plus 4 is 5. Plus 4 more is 9. Plus 4 is 13. Plus 9 is 22. I'm just going to kind of write that down so I can continue on. 22 plus 4 is 26. 26 plus 16 would be 42. 42 plus 4 is 46. 56, 66, so 75. So if I go ahead and actually add that all together, it equals 75. So when it tells you to evaluate the series, you need to write out the sum, but then you actually evaluate it. Okay, on the second one, I'm going to go from 0 to 3. I'm plugging 0 in where a is. There's a 2 times here, so I'll plug it in both. So 0 times 0 minus 7. Then I'd go to 1 times 1 minus 7. 2 times 2 minus 7. And 3 times 3 minus 7. So now I just evaluate each of these. Remember, I need to think about order of operations. So I'm going to go inside my parentheses first and multiply it by the number out front. So 0 minus 7 is just negative 7, and negative 7 times 0 is 0. So that term just goes to 0. 1 minus 7 is negative 6, and negative 6 times 1 is negative 6. 2 minus 7 is negative 5, and negative 5 times 2 is negative 10. And 3 minus 7 is negative 4, and negative 4 times 3 is negative 12. So negative 6 minus 10 more is negative 16, and negative 16 minus 12 equals negative 28. Okay, so that would be the sum added all up, right? I evaluated it to get the answer. All right, so now the last one, I have 49 minus k. K goes from 2 to 5, so we're going to start at 2, end at 5. So 49 minus, whoops, not k, minus 2, plus 49 minus 3, plus 49 minus 4, plus 49 minus 5. So if I go ahead and evaluate this, I'm going to get 47 plus 46. Actually, you know what? When I'm doing this, I need to make sure that I go left to right. So I should just, since everything is addition and subtraction, there's no multiplication here, I really should just work left to right here. So 49 minus 2 is 47. 47 plus 49 would be 80, 96. 96 minus 3 is 93. 93 plus 49 would be 142. I'm just trying to keep track of where I am here. 142 minus 4 is 138. 138 plus 49 would be 187 minus 5. So that would give me 182. And of course you can use your calculator for this too, once you have them all listed out like that. Okay. So now we're going to go the other way. We're going to look at a series that's written out as a sum in longhand, and we're going to use sigma notation to write it out, okay? So my note here says, to write a sum in sigma notation, try to find a formula involving a variable k, where the first term can be obtained by setting k equal to 1, the second term by k equals 2, and so on, right? So we're trying to find a formula so that when I plug in k equals 1, it gives me a 2. When I plug in k equals 2, it gives me 4. When I plug in 3, it gives me 6, 4 gives me 8, 5 gives me 10, 6 gives me 12. So because I'm starting at 1, and so this would be 1, 2, 3, 4, 5. So these are just my index numbers, right? So I know it's going to end at 6. Now I need to think of a formula that gives me that. So if I were to take and plug 1 into a formula and I need it to equal 2, and I know that these are each going up by 2 each time, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8. So if I just do 2 times k, this should give me that series. So if I plug in a 1 for k, I get 2. If I plug in 2, I would get 2 times 2, right, which is 4. If I plug in 3, I'm getting 2 times 3, which would give me the 6. So I think that would work. Now, I mean, this is a guide here to start at k equals 1, k equals 2, k equals 3. That is a good idea, but this is not the only way to write this series. You could do other things. So I guess if you want to do it differently than I did it here, you can. All you need to make sure is that when you put in your first number, it gives you the first term. When you plug in your second number, it gives you the second term. And then that it ends at this term right here. So if you come up with either a different formula or a different starting and ending point, as long as it works and is true, and every time you plug in one of your index numbers, it gives you the right thing, it doesn't have to be exactly the same as this, okay? So on this next one, it looks like, so this is, I'm just going to put my index numbers below again, just trying to think about. So I've got a 1, a 4. My first term, when I plug in a 1, I need to get a 1. When I plug in a 2, I need to get a 2. When I plug in a 3, I need to get a 4. When I plug in a 4, I need to get 8. When I plug in 5, I need to get 16. And when I plug in 6, I need to get 32. So I'm not seeing a real obvious way to do that. It's not the same. It's not going up by the same amount each time, right? So what I am noticing is that like this first one. Well, let's skip the first one for a second. This one right here is 2 to the first power. This one is 2 squared. This one is 2 to the third power. 8 is 2 to the third. 16 is 2 to the fourth. 32 is 2 to the fifth power. So I can kind of see that I have my index numbers are going up here, and that's giving me the right thing each time. So maybe instead of starting at 1 here, I could start at 0, 2 to the 0 power. So I could go ahead and start at k equals 0 and go to k equals 5, right? 1, 2, 3, 4, oh, so 6. Yeah, but it would be 5 because if I start at 0, I would need to go to 5, not 6, right? 0, 1, 2, 3, 4, 5. So instead of starting at 1 like I was originally thinking, we're going to start at 0. You could still start at 1. In order to do that, we're going to be doing 2 to the k power here. In order to do that, I would need to write k minus 1 here, so that it started at 1 and ended at 6. But I subtracted 1 from k each time, it would give me the same thing. But starting at 0 is perfectly acceptable also. Okay, so if that didn't make sense to you, I could have instead written it like this and got the exact same thing. It goes from 1 to 6, and 2 is raised to the k minus 1 power. So that when I plug in 1 here, I actually get 2 to the 0 power. When I plug in 2, I actually get 2 to the first power. So that it does give me the correct result, right? 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. Okay, I need each term to come out correctly, but you might be able to adjust where it starts and stops, and the formula may be adjusted a little bit to make that work. So you just got to be thinking about it. Does it actually give me the same series? If yes, then it works, and it's great. All right, so this next one here, again, I'm wanting to plug in 1, then 2, then 3, then 4, and then 5. Again, this one's not going up by the same amount each time, but if I think about this, these look like they are related to the number somehow. So 125 and 5, 64 and 4, 27 and 3. Like these are all multiples of these numbers. And it looks to me like perhaps the number is cubed. Let's just check that. So if we cube all of our index numbers, do I get these numbers? So 1 cubed is 1, 2 cubed, 2 times 2 is 4, 4 times 2 is 8, so that works. 3 cubed is 27, 4 cubed, 4 times 4 is 16, and 16 times 4 is 64. 5 times 5 is 25, and 25 times 5 is 125. Yeah, so that works. So notice my index number, one that's going up from 1 to 5 is on the bottom in this case. So we'll call k or I or n, doesn't matter which variable you use, that'll be our bottom number, and then we're going to cube it. And then k is going to go from 1 to 5. Okay. Okay, and then lastly, we've got 50 plus 51 plus 52 plus 53. So it looks like each of these is just going up 1. If this is number 1, 2, so again, I'm writing out my index numbers. You can start at 1, you can start at 0. It might be easier on this one to start at 0. I'm not sure. But let's go ahead and start at 1, so let's use n this time. So n is going to go from 1 to 6. I need to get 50 when n equals 1. So let's do, well, what if we just did 49 plus n? Okay, again, I could start at 0 and then do 50 plus n. But, so either one of those would be correct and accurate. You've just got to be thinking about what works. Okay, and if you've got to plug it in and make sure it works. So if I plug in 1 here, I'm going to get 50. If I plug in n equals 2, I'll get 51. If I plug in n equals 3, I'll get 52. So this works. Now, if you wanted to start at 0 instead, just to point out, it doesn't have to always look exactly the same, but it can still work. And then do 50 plus n. Okay, so if I put 0 in there, I'm going to get the 50. If I put 1 in there, I'm going to get 51. If I put 2, I'm going to get 53 up to 55. So that works too. So you can adjust it a little bit. Make sure you're trying it and plugging it in and making sure that it works each time. Okay, let's see. I guess that was it. So good luck with trying those on your homework. Just shoot me an email or talk to me in class if you have any questions, and we'll see you next time.